So we're continuing some results that we started to look at a couple of weeks ago, and these refer to the family of inparabolas, to a circle-inscribed Poncelet family of triangles. So I have here my circle-inscribed family of Poncelet triangles, and I'm drawing the family of inparabolas with respect to a fixed point f on the circumcircle. I'm also showing here, let's pick a good position here, let's go back here a bit. I'm also showing here, so besides the inparabola, the vertex of this inparabola, okay, and the axis of the inparabola. Okay, so you can think of the vertex as a perpendicular projection on this line here that is tangent to the inparabola at V. Okay, so it's a perpendicular projection on this line. It turns out this line is congruent or coincides with the Simson line, as I was reminded by my friend Liliana Gheorghe. So this line here, this line that is tangent to the inparabola at V, is also the Simson line, or the Wallace-Simpson line, of this triangle with respect to f. That is to say, this is the line that passes through the three collinear vertices of a paddle triangle computed with respect to f. Okay, so if a point is on the circumcircle, the paddle is going to be degenerate. It's going to be that straight. It's going to have three collinear vertices, and that line is called the Simson line. So you can think of this as a line that is tangent to the inparabola at the vertex, or you can think of it simply as the Simson line of this triangle. Okay, and V now becomes the perpendicular projection of f on the Simson line. And this is an object that is not very often studied. Folks study the Simson line, but they don't study the perpendicular projection of the point on the circumcircle on the Simson line itself. All right, so of course I can play around with f, right? And I'm going to get a different Simson line, and I'm going to get a different perpendicular projection. I'm still calling it V, okay? Just to remember that this is also the vertex of the inparabola with focus on f. All right, so last week, or a couple of weeks ago rather, we actually saw this very interesting phenomenon, which was for certain Poncelet families we had been playing with, the locus of the vertex over Poncelet was a circle. So what this new video is showing is that this locus continues to be a circle on a generic circle-inscribed Poncelet, meaning that my inconic is in general position. So this is the inconic over here. So let's now play with f. Let's place f somewhere else, and you're going to get a different circle. Now notice that the circle is in general not tangent, okay, to the inconic, as it's usually the case, or it's actually always the case, if your inconic is concentric with the circumcircle, then you get continuous tangency. So what this video is about is let's actually look at this family of circles as I move f. Right, so now it's been established that the locus is a circle, and I'm just looking at the family of circles that you get as you move f around. Okay, so what I did here was, just to actually illustrate this, is I can actually draw a family of circles corresponding to the sort of sweep of loci over f, right? So these green circles here, they're nothing more than the sweep of f over all points in the circumcircle. And one thing that you notice here is that, first of all, I don't know if this shape here, the outer envelope of the shape here, is an ellipse. It doesn't look like it's one, right, because it's bulging over here. Okay, and I don't know if the inner envelope of this thing is elliptic, although it does look like one. Okay, but the first striking remark here is that the center, so the curve that is swept by the centers of my circular loci, right? So remember that each one of these loci is obtained via a complete revolution of the Poncelet family. Now, all I'm doing here is, okay, I understand that already. Now let's sweep f over the circumcircle, and let's see what the corresponding circles do. And what you're looking at here is that seemingly the path of the center of these loci, represented here by these green circles, looks like an ellipse. And it is an ellipse. It's numerically an ellipse. Let's turn off the green circles, and let's just show, well, let's just show, the abstract locus of those centers over there as I jog F on the circumcircle. And you can see here that the center of these magenta circles is following a perfect ellipse. It doesn't look like this ellipse is axis aligned with the inconic. It's not concentric with either the inconic or the circumcircle, but it is an ellipse in its own right. And while we already have a proof that this particular locus here is a circle, we do not yet have a proof that the locus of the center of the circular loci is an ellipse. So this is sort of a meta locus, right? And that's pretty cool. Now I think I have one more result here. Yeah, let's turn off this locus here. And now I want you guys to take a look at a curious phenomenon about the Simson line, the envelope of the Simson lines over Poncelet. So one notices here that wherever we place F, so let's place F somewhere else, you're going to get a different, over Poncelet, right, a different circle for the locus of V, of the vertex of my inparabola, or that perpendicular projection on the Simson. But one thing that you notice is that W is a point through which all the Simson lines pass. Equivalently, you could say that the envelope of Simson lines over Poncelet is this point W. And this point W happens to be the reflection of F about the center of the locus. So they are antipodes. F and W are antipodes wherever you place F. Okay? So another question you can ask is, overall F, since these point W's are uniquely associated with F, what is the locus of F, right? What is the locus of W? So what is the locus of the antipodes of F on the circular locus of V? And we can draw that as well. And it just so happens that this guy is also an ellipse. It's this orange ellipse, which seems nicely concentric with the inconic, but it's not axis aligned with the inconic. So the locus of that envelope of my Simson lines, that point W, is the orange ellipse, concentric with the inconic, but not axis aligned with it. Okay, so here we are. We have two new ellipses, the locus of the center of my circular loci of V, the magenta ellipse, not axis aligned, not concentric. And now we have the locus of W, which is the envelope of the Simson lines over Poncelet. So the locus of W over F is the orange ellipse. So I think that what this video is hoping to show is that we keep most of those properties that we were seeing in sort of canonical Poncelet families, even when you let a generic Poncelet be studied, meaning that a generic circle-inscribed Poncelet be studied, meaning that its inconic is in general position with respect to the circumcircle. So I hope you guys enjoyed this video, and I'll see you in the next one.